last class we have been discussing about this different modes of AFM. So, we also had some discussion about this the concept of fiber pulling with different mechanisms. So, as far as this fiber pulling is concerned, it is a kind of quite an interesting manipulation. So, this by deploying this manipulation appropriately, we can have a control over the fabrication of these fibers. These fibers has a potential application in different fields, okay, like especially as far as these fibers are concerned with reference to micro robotic perspective point of view, these are being effectively used for different sensing elements. In fact, like the mechanism which is evolved which with reference to AFM based fiber pulling, like those mechanism can also be deployed for manipulating a micro robotic system. So, we have discussed about the different types of like micro nanofiber pulling. So, one of the micro fiber pulling involves AFM, the other one involves a kind of a flame heated taper drawing, another one involves a kind of a tungsten probe based pulling, where we have a kind of a liquid layer through a pulling through a liquid layer, a kind of a like manipulation is applied in such a way that the tungsten probe is made to touch the liquid, and then when we try to pull it, you get a kind of a fiber which is being exerted from the system. Then there is a polymer drawing system is there. Through this polymer drawing, we can just integrate it in the inside the molten polymer, and then when we try to pull it, you get a fiber coming out of it. Okay. So, we have been discussing about the different applications of these fibers. So, one of the application include the gas absorption spectroscopy, the Mach-Zehnder interferometer, then the gratings which are involved, the resonators, and there are some couplers which are being involved. So, when we try to look into the couplers, so one of the configuration of the coupler involves that like there are two sets of ports which are being used and which is used for monitoring perspective point of view. On an application perspective point of view, it is highly used for optical sensing, biosensing and feedback related systems. Okay. So, now we can also consider an application which is called as a tweezer. So, as far as tweezer perspective point of view, mechanical tweezers have a kind of a manipulation in the order of few microns order. When we try to exert a force on top of it, appropriately we can see a kind of a manipulation which exerts and which can be used for movement of the system. So, as far as these in the case of fiber perspective point of view, if you see the overall construction of it, so there is going to be an optical fiber and then there is going to be a taper region, and in between that whichever system needs to be manipulated. So, appropriately when we try to have a control over this optical fiber, then we can manipulate the structure. So, if we try to look into the classification based on the configuration, so one is called as a dual fiber optic tweezer and the other one is called as a single fiber optic tweezer. In the case of a dual fiber optic tweezer, we have two taper region and then there is a this system in place. Appropriately by manipulating it, we can have a control over the structure. In the case of a single fiber optic tweezer, so we can have a control over a manipulation over a particular point. So, these taper fiber tips can be produced by either chemical etching or heating and drawing. The principle of tapping a particle in a stable conditions between a dual beam tweezer is balance of the scattering force in axial direction and a centripetal force in the radial direction. Like when there is a kind of a slight unbalancing of these optical forces, this will result in a kind of a motion of the particle. So, when the ratio of the optical power from two fibers are adjusted, then the particle will be pushed to the side with a weaker optical power until a new balanced position is formed. The single fiber tweezer works on a gradient trap on a tight focal spot near to the fiber tip, and tweezers are used for trapping and manipulating the biological samples based on the need or based on the application. Now, as far as this optical tweezers are concerned, so it has an effective applications, especially with reference to the micro manipulation perspective point of view. So, like when we consider such kind of optical tweezers, these optical tweezers has a potential application with reference to optical towards the micro robotic perspective point of view. Like so, So, now we will be discussing about this optical manipulation, especially the usage of optical tweezers for micro robotic related applications. So, as far as these optical micro robots, like as far as when we try to consider these optical tweezers, this optical manipulation technology that enables an accurate manipulation of micro robot even in a kind of a fluidic environment. That is one advantage of this particular system. So, these optical micro robots, which can be used as a kind of a micro tool to perform an indirect micro object manipulation via optical tweezers, and it has been employed for various biomedical applications. So, like the support by the latest advances in 3-dimensional microfabrication, micro robot with sophisticated structures can be created with good reproducibility and yield, further expanding the use of optical tweezers for manipulating micro robots. Now, as far as in this particular field is concerned, the optical system, the optical it can also be called as optical micro robots. These optical micro robots can be fabricated using a shape change material. So, of course, related to this shape change material, we have discussed in some sections where we have used a kind of this optically sensitive polymers, so that these optically sensitive polymers are capable enough in such a way that it gets actuated when the light falls on it. So, these optical micro robots can be fabricated by using a shape change material such as light sensitive polymers, and the deformation of the materials can lead to deformation of micro robots, a kind of a body component, and therefore, they can control the movement of micro robot. However, this mechanism is difficult to enable a 6 degrees of freedom, like a kind of a dexterous manipulation of micro robot, as the material property can be non-linear, which makes it difficult to ensure the precision for a closed loop control. Now, another popular optical manipulation method is to leverage the momentum carried by the laser beam to enable the optical trapping of micro objects, which is a basis of an optical tweezer. So, when a scale below 100 micrometer and the force generated by the light induce a mechanical effect becomes the significant part of this particular system. Now, when we try to introduce this optical micro robots, so it is a kind of two fields are coming into picture. So, one is a kind of a photonics field and other one is the kind of a robotic field which comes into the picture, and finally it is so it will try to create a kind of a micro devices what we are looking for. Now, let us discuss in detail about this kind of optical manipulation. So, let us take a small a block diagram about this optical manipulation. So, let us consider our input parameters are the perception, which is nothing but the sensing, and then the output is in the form of manipulation, which is a kind of a control. Now, this is a kind of an interaction which exhibits between the robotic techniques. Now, if we closely observe the different interactions, so there are 4 different modes which come into existence. One is based on the light type, which ideally includes the UV light, a visible band and the infrared. Now, when we try to talk about the scale, we have the micrometer and the nanometer in place. Similarly, when we try to talk about the control modes, so one important aspect is with reference to the optical trapping, and the other one is the light responsiveness. With reference to robot material perspective point of view, we have the polymers, metal and organic matter. So, like when we try to closely observe in this particular system, so these are the different parameters which are being deployed with reference to this optical based tweezers, etc. Now, let us see two important modes of this optical based system. So, like which is used for a micro robot related applications. So, one mode which involves, let us see the schematic. So, we have a multiple beam splitter in place. So, this is a kind of a conventional optical tweezer system which can generate a multiple laser spots based on the time sharing. So, there is going to be a probe laser and then there is going to be a fiber laser. From a probe laser, we have a deflector, and from the fiber laser, there is going to be a deflector. Through this deflector, it moves through a system called AOD, which we call it as acoustic optical deflector. Through this acoustic optical deflector, the light passes through the system with an appropriate optics, and the beam get deflected through a lens arrangement, and then there is going to be a sample, and we have the, through this we have the illumination. So, this is a kind of a motorized stage which exhibits, and here also we have a deflector. Through a deflector, there is going to be a lens which will get integrated into it. So, in this particular system, we have two lasers in place. One is called as a probe laser and other one is called as a kind of a fiber laser. It passes through an acoustic optical deflector, and then when it passes through an objective lens through the motorized stage, we can see a kind of illumination. So, ideally, so it can be used, like suppose we have a structure something like this. These structures can be oriented using such kind of system. So, by the movement of this acoustic optical deflector, so appropriately we can have a kind of a orientation. So, this is a kind of a simple system. So, this system is called, it has a capability to generate multiple laser spot with the time sharing okay, and it can generate a kind of a dexterous manipulation for optical micro robots. Right, which is used by the conventional system. Now, let us discuss about the next configuration, which we call it as a kind of a, so here this is a kind of a motorized stage and this is a objective lens, this is a sample which is placed and there is a kind of an illumination characteristics which exhibits. Now, let us discuss about the next configuration, which is called as holographic optical tweezers. So, as far as in this holographic optical tweezers are concerned, it can generate a kind of a multiple laser spots and it is used for like kind of a manipulating a micro robot in the required plane. Okay. So, if we see the overall construction of it, there is a visible light source, mirror, sample, this is fed to a mirror which is integrated with the CMOS camera. There are two dichroic mirrors are there. One dichroic mirror is like this and the other dichroic mirror is like this. And then there is going to be a kind of a spatial modulator, where from the sample through the spatial modulator, which we call it as SLM, there is a IR laser is there. This is going to be a kind of a CMOS camera. So, as far as in this particular case is concerned, we have a kind of SLM is called as spatial light modulator. So, like in this particular case, like what we are trying to see is a kind of a it's a kind of a time sharing with a spatial position control with a kind of optical tweezer in a straightforward, and several micro objects can be trapped. Like for instance, if we have a particle 1, particle 2 and particle 3, these particles can be easily trapped using this particular system and it can be transported to the target areas. So, trapping multiple part of a structure via different focal point has been used to control the planar rotation of a micro robot. However, the out of phase orientation control is difficult to implement, since the focal point of the optical laser traps are constrained in the same focal plane, with a special design of a micro robot, which is required to achieve a kind of an out plane manipulation. So, let us discuss about the overall system configuration of these kind of optical tweezers. Okay, so that is like a different process which are deployed with reference to automation of this particular system. So, if we see some of the key components which are involved for this for automating this optical tweezers are concerned, like one is, let us consider this as an optical tweezer. So, the one of the key input for this optical tweezer is the real time motion control. So, where there is a laser beam focal position and velocities are placed, are integrated, and then we have a kind of a working image where the perception, which is a kind of an image processing which is deployed, and this is the kind of a workspace image. So, from the perception, one of the aspect goes to the manipulation, and the other one goes to the path planning, and from the manipulation we have the system design modeling, which is being fed into this path planning process, and from the path planning process it is fed into the real time system. So, if we closely observe, like we get the feedback from this optical tweezers for a kind of an efficient operation, like to understand the influence of different operation parameters. Appropriately, the system design will take up the shape, and system design will model the system, and from the modeling the inputs are fed into the path planning, and from the path planning again it is going to the real time motion control. So, here if we try to, so this will help us to have a kind of a collision free trajectories for cells for the objects or cells to reach the particular position, sorry, to reach the particular position. Now, we have the operation, and then whatever objective constraints are there, that it is being fed into this path planning. Are appropriately fed into this path planning, and the estimated location and orientation of the cell are observed in this. Are measured in this. Now, if we try to look into the overall fundamentals of this system, like whenever we are trying to model these fundamentals of the system, some of the key parameters which we may need to consider. So, let me just list down the list of key parameters. So, affecting the overall performance of optical tweezers are, one is this states bead position and appropriate control inputs. The optical trap, which is nothing but the laser beam focus. Second is the linear and the non-linear spring stiffness, parameter, towards axial and radial components. Third is the thermal forces, which is ideally modeled using a kind of a Gaussian distribution. And the fourth is the kind of the viscous drag, buoyancy, and the inertial forces are considered appropriately. Okay. So, these are some of the key parameters which are affecting the performance of an optical tweezer. So, whenever we are designing such kind of optical tweezers for different manipulation related applications, these are the parameters which we may need to consider.